Hi students, in this video we are going to study about compound microscopes, the microscope which we have used in laboratories. Now, compound microscope it is an optical device which is used to magnify tiny objects, very tiny objects which we cannot see using our naked eye. Compound microscope basically consists of two convex lenses, and each convex lens is known by their name. So, it consists of parts. It consists of two convex lenses which are arranged coaxially. Coaxially means what? Along the same axis. Coaxially at the ends of two sliding tubes. So, there are two lenses, two convex lenses, and these two convex lenses are known by the name. First one is objective. So, from the name itself it is clear, objective means the one which is close to the object. It is a convex lens of short focal length and small aperture. The lens is short focal length and small aperture, which is placed near to the object. Second one is known by the name eyepiece. Eyepiece means the one which is close to our eye, and it is also a convex lens of comparatively large focal length. Comparatively large means it is not a very high value, but when compared to the objective, the focal length of the eyepiece is little more, of large focal length and large aperture that is placed near to the eye. So, we have the objective and we have the eyepiece. Objective means the one which is placed near to the object, of shorter focal length and short aperture, whereas the eyepiece means the lens which is placed close to the eye, our eye, which is having a comparatively, when compared to the objective, is having slightly more focal length and larger aperture. Okay. Now, we are going to see in the, like the previous video, like the case of simple microscope, we are going to see when the final image is formed at infinity or when the final image is formed at the near point, that is the least distance of distant vision, what is the equation for magnification of a simple microscope. Okay. So, case 1, when the image, final image is obtained at the least distance of distinct vision. I am going to write it as D. Okay, least distance of distinct vision. So, first let us write what is the equation for magnification. An equation for magnification is ratio of angle subtended by the image to at the eye, ratio of angle subtended by the image at the eye to angle subtended by the object when both are at the least distance of distinct vision. So, it is an angle subtended by, like the first case of simple microscope, it is a ratio of angle subtended by the image at the eye to the angle subtended by the object at the eye when both the image and the object are imagined to be placed at the least distance of distinct vision. So, let us see how to draw the ray diagram in this particular case. So, this is our optic center, principal axis. Here is our objective of comparatively smaller aperture, and we have the eyepiece having larger focal length comparatively and large aperture. Now, what is happening here is, imagine there are two lenses, and one lens, the object is placed in the front of first lens, that is the objective, and this objective forms an image. That image acts as what? Acts as a virtual object for the eyepiece or the second lens, and we get the final image after refraction, after the ray passing through the eyepiece. After refraction, we get the final image at least distance of distinct vision. Now, here the eyepiece, the working of eyepiece you consider same as that of a simple microscope. That is, the object for the eyepiece should be between the focus and the optic center. The object for the eyepiece should be between the optic center and focus of the eyepiece. For that, the object is placed, the real object, we call it as AB, is placed beyond the focus of the objective, and the ray of light after refraction meets at this point. Okay. Now, this once more. We have the objective and the eyepiece. Now, object, the real object, is placed beyond the focus of the objective, and the ray of light after passing through the objective forms a real inverted enlarged image between the focus and optic center of the eyepiece. Okay, this is the focus of the first lens. Now, this distance is the object distance, we take it as u0. This is the image distance for the object, take it as v0, and this distance to the optic center is the object distance for the eyepiece, we will call it as UE. Now, what happens now? The object, this image acts as what? It acts as an object for the eyepiece, and the ray of light passes through the eyepiece. Since it is placed between the focus and optic center, they won't meet. So, we trace the ray, and the final image, is formed at this particular point, which is at a distance d from the optic center of the eyepiece. I hope this is clear. The object is placed beyond the focus of the objective. The ray of light after passing through the lens meet at a point which is between focus and optic center of the eyepiece. Okay, from there the ray of light passes through the lens after refraction. They are not meeting at a point, so we retrace the rays and we get the final image, a well defined, well enlarged image on the same side of the object. This is AB, this is A dash, B dash. It is having a height h dash. The height of the object we can take it as h, and final image we can take it as h double dash. Now the angle made, so we are viewing the object from here. So the angle made by the eye to the image, this angle is taken as beta, and alpha we are drawing it separately like before. If AB is the object, we are viewing it from the least distance of distinction D. So this angle is alpha and h is considered to be the height of the object. Okay, I hope this diagram is clear to you. I will explain it once more. We have two lens, objective and eyepiece. The image objective which has to form the final image is placed beyond the focus of the objective. The rays after refraction through the lens meet us at a point which is between the focus and optic center of the eyepiece. From there again the rays get refracted through the eyepiece and we get the final image at a distance D from the eyepiece. Now UE is the U0. U0 is the object distance, V0 is the image distance of the objective, U is the object distance of the eyepiece, and D is the image distance of our eyepiece. Now this is clear, and in order to find out what is tan alpha, we have drawn it separate, the diagram separately. So this is figure 1, this is figure 2. Like the previous method, we will find out what is tan alpha, what is tan beta, and we just substitute in the main equation. So magnification M is equal to tan beta divided by tan alpha. Now from the figure 1, tan beta is what? Tan beta is this from this triangle we get tan beta is equal to A dash B dash divided by B dash O, which is equal to what? What is A dash B dash? We are getting an inverted image, isn't it? So A dash B dash is minus H dash, and what is B dash O? B dash O is minus UE. So we get this as A dash B dash by B dash O is equal to minus H by UE, that is H dash by UE. Minus and minus get cancelled. This is equation 1. Okay. Next, from figure 2, we are going to find out what is tan alpha. From figure 2, tan alpha is equal to opposite side by adjacent side, that is AB divided by BO, and what is AB? It is H and BO is D. So this is equation 2. Now substituting the value of equation 1 and 2 in the main equation, M is equal to. So substituting equation 1 and 2 in M is equal to tan beta by tan alpha, we get tan beta is equal to H dash by UE divided by H by D. On rearranging this, we get this as H dash by H into D divided by UE. H dash by H into D divided by UE. Now H dash by H, you are familiar with that equation. What is H dash by H? It's actually the magnification equation to find the magnification. Now what is H dash? H dash is the image, height of the image of produced by objective, isn't it? And H is the height of the object in front of the objective. Or we can say H dash is the height of the image and H is the height of the object, which means H dash by h is the magnification produced by whom? Produced by the objective. And also d by ue. Now d is what? Sorry, d is what? D is the final distance, isn't it? Image distance of eyepiece, and ue is the object distance of eyepiece. So image distance by object distance is what? Again magnification. So magnification produced by whom? Magnification produced by the eyepiece, which means for a compound microscope, if the final image is obtained at the least distance, then magnification M is the product of magnification produced by the objective into magnification produced by the eyepiece. M is equal to M0 by ME, which is h dash by h into d by ue. Now it is difficult to measure the height of the object and image. Now we have modern technology, but still h dash and h is difficult to measure. So we are going to convert h dash and h into image distance and object distance. So we can write h dash by h. We know using lens formula we derived h dash by h in terms of v and u. It is v by u. Since it is magnification produced by the objective, we can write it as v0 by u0. And also if you look into this diagram, you can see the eyepiece is doing the same function. The eyepiece is doing the same function as that of the simple microscope. Okay, which means d by ue, using the mirror formula, you can write it as 1 plus d divided by fe. D by ue is equal to 1 plus d by fe. If you want, I'll show you. This equation 1 by v minus 1 by u is equal to 1 by f. In our case, v is final image distance, that is minus d. U is object distance of the eyepiece, that is minus ue, and f is the focal length of the eyepiece. Since there are two lengths, we are denoted by fe. So we get minus 1 by d minus 1 by minus ue is equal to 1 by fe. Now on rearranging, we get d by u, and rearranging and multiplying with d, we get d by u is equal to 1 plus d by fe itself. So the final equation for magnification produced by a compound microscope is m is equal to v0 by u0 into 1 plus d divided by fe. This is the magnification produced by a compound microscope if the final image is obtained at near point or at the least distance of distant vision. Now there is a special condition. Now if you look into the diagram of ray diagram of compound microscope here, you can see the object is placed very close to the focus of the objective, which means we are doing a certain approximation as the object AB is placed very close to the focus F0 of the objective. We can write u0 is equal to minus F0. It is approximately equal to, not equal to, approximately equal to minus F0, and V0 is equal to L, where L is known by the name tube length. Tube length is the distance between two convex lens, that is the distance between the objective and the eyepiece. So magnification equation can be written as m is equal to minus f0 by L into 1 plus d divided by E. Now this equation is used only for the special condition to solve problems, okay, which we will be doing in your online class. So I hope this derivation is clear to you. It's very simple. Just make sure that the ray diagram is correct, and when you are drawing the ray diagram, the object should be placed in front of the objective beyond the focus, and the image of the object should be formed between the optic center and focus of the eyepiece. Then rays from the image which acts as a virtual object for the eyepiece passes through the lens. After refraction, they won't meet at the point, so we retrace it back and we get a very enlarged inverted image on the same side of the object. Then what we do, we find out what is tan beta from the diagram and tan alpha using a separate diagram. Substitute it, we get m is equal to what, h dash by h into d divided by ue. That is the equation for magnification, and we find that h dash by h means magnification produced by the objective, d by u is the magnification produced by the eyepiece. So what is the next step? We convert h dash, h, d and ue to the known value, and h dash by h is v0 by u0, d by u is 1 plus d by fe. Substitute, we get the final equation as m is equal to v0 by u0 into 1 plus d divided by fe. And for special condition, since the object is placed very close to the focus of the objective, we write u0 is equal to approximately equal to f0 and v0 is equal to L, which is the tube length, and the equation becomes m is equal to minus f0 by L into 1 plus d divided by fe. I hope this derivation is clear to you. Thank you.